Hello, everyone. My name is Satoshi Matsuoka, and I'm the director of Riken Center for Computational Science. Today, I would like to talk about Fugaku, the supercomputer that we have been developing for 10 years. This is the first exascale supercomputer and the most versatile supercomputer in the world. And I also want to talk about what kind of bright future Fugaku can help to realize and how it is contributing to solving the problems of COVID-19. The name Fugaku, as you know, is the other name for Mount Fuji. And we gave this supercomputer this name Fugaku because we want to show the two ideals that we want this supercomputer to have. First, Mount Fuji is the highest mountain in Japan, so it has very high peak, high performance. And with that, we want to solve the problems, the social and scientific problems that we have never been able to solve before. But also Mount Fuji, as a single mountain, has very broad base. That's why it's so beautiful. So we want this supercomputer to have very broad base, and not just for some applications and scientists. It should support a lot of applications and programs so that we can contribute to the society. That's why we gave the name Fugaku to this supercomputer. Fugaku is obviously the fastest and the largest supercomputer ever built in the world. But we didn't develop this computer just to achieve the largest or fastest in the world. Rather than that, we had the application-first principle in developing Fugaku. We were not fixated on achieving number one in the world. As name shows, we wanted the very broad base applications to be supported with this high performance so that we can solve social problems. So we had the application-first spirit in mind when we developed this. But for that, we need to meet certain requirements. Before Fugaku, it was K-computer, and K-computer was large machine. But just evolving K-computer would not be enough to meet the performance requirement of Fugaku. So compared to the past, we needed to develop innovatively fast CPU. And not just the speed, various applications have to run on it. For example, Line apps is running on smartphone. So even Line app should be able to run on Fugaku. So high general purposeness and high performance and high power efficiency needed to be achieved at the same time. And that became possible thanks to the moonshot type of development structure. Our science of computing in Japan, the computer science arena, and science by computing. So by using that computing power, what kind of issues we are going to solve. So all Japan community collaborated. For example, in 1961 in the US, John F. Kennedy said we will go to the moon. And with a national project, they were able to send people to the moon in 10 years. In 2010, in Japan, with the inception of the concept of Fugaku, we spent the 10 years to develop. And all supercomputing community in Japan were united to develop Fugaku. And each CPU performance compared to other top CPU in HPC apps, it's 3 times higher performance and 3 times higher power efficiency. And ARM CPU, it understands the ARM instruction set that is running on your smartphone or tablet Recently, there's a PC that was developed, but same instruction can be understood. So Linux, Windows, or PowerPoint, and even Line app would run on Fugaku. So that kind of general purpose ARM CPU was developed. And since the inception of Fugaku concept, there's the emergence of a new arena, AI, and we need acceleration features for AI. And Fugaku has several hundred petaflops and exascale. So if we convert it to smartphone, it's about 20 million smartphones. And the backyard, it's supported by a high-performance server in the cloud. And in terms of the number of servers, it's equivalent to 300,000 servers. Coincidentally, it's about the same as the annual shipment in Japan. So if we have 2 or 3 Fugaku, it covers the entire annual IT in Japan. As I said before, we spent 10 years to do research and development of Fugaku. Back 10 years ago, it was when the Project K, the K computer, was starting. But due to the government budget reduction, we faced some challenges. But even so, we were thinking about the new machine, and we started the project. And after ups and downs, fortunately, in 2020, we installed Fugaku. We still have to develop software, so the official launch would be next April, but the installation has been already completed. So some applications, especially for COVID-19, are already running on Fugaku so that we can contribute to the society. As I've said before, we developed Fugaku with applications first mindset. So in 2020s, just purchase CPU and put that in supercomputer will not be enough. So we worked collaboratively with the computer science arena and application side to proceed with the development. And our center played a very important role. Our target is to achieve up to 100 times higher speed up compared to K computer. And this 100 times is not just a nominal number. The people from application side said that in order to achieve next breakthrough, the speed has to be 100 times faster. As a result, we came up with this A64FX, the latest CPU. With a national project we developed with taking a lot of risks. We developed and adopted latest technologies or technologies that were not be used in the conventional CPUs, and with that we achieved high performance. And the A64FX CPU takes a lot of time if I go into the details. So just give you the overview. So this CPU is a many-core CPU, and it achieves two characteristics at the same time. So it's like a chimera type of CPU. So it's a many-core ARM CPU. So it has 48 compute cores and 2 or 4 OS cores, so the total of 50 or 52. And each would understand the V864 instruction, and it's scaled, so regular software can run. So and each core is pretty fast. Compared to the server side CPU, it's about the equivalent speed. So in a way, this has the characteristic of regular CPU, although it has many cores. But also at the same time, with this core and the entire memory subsystem has the architecture of GPU or vector supercomputer. So compared to regular CPU, so it has the memory bandwidth or network bandwidth of the GPU or old type vector supercomputer. And with that, large amount of data would be streamed. Then to each element, the vector processing can be done. And that vector can handle various data type, not just for HPC, but also for AI. With that, so this CPU would work as regular CPU for general programming, but for HPC or AI processing, when we need vector processing, it can work as like a GPU, and it would have like a high bandwidth vector processing. So it's not that the GPU is separately installed inside. Each core would have the characteristic of both CPU and GPU. And those cores are connected with memory subsystems or chip network at high bandwidth. So that's why the structure is quite different from regular CPU.
So most recent many-core architecture, ring-bus network on-chip or mesh topology is used to connect the core-to-core. But for this chip, 4-core memory group are in 13 cores multiplied by 4 regions, and those regions are connected with ring bus. And inside the CMG, it is completely cross-connected, as you can see in this graph. So those who understand architecture can tell how it enables a high bandwidth processing, especially at cache coherent operations. And at the same time, Tofu D that we developed this time realized how high bandwidth and extremely low latency as the chip is connected with internal path. It's not connected via PCI, so high bandwidth as well as low latency is achieved. Though I do not mention in details, all chips combined have tens of terabytes bandwidth internally. And externally, it has 1 terabyte per second memory bandwidth. And moreover, as Fugaku is consisted of about 160,000 processors, each CPU must have extremely and super high reliability. Ordinary computer CPU reliability simply does not work. As Fujitsu have been developing mainframe so long, each chip has mainframe level RAS. And some same mechanism existed from K-computer, and since then reliability is 4 times or 10 times higher compared to the usual server CPU. So therefore, even with 160,000 CPUs are combined and 160,000 processors operate same software, it works properly under the best case without any faults. With that kind of configuration, of course, we have very fast against the benchmark. And what we are comparing here is that comparing high performance general purpose server, especially with high-end model, versus our A64FX1 chip. And server in the market, normally a dual socket model, so this is 2 chips. So we are comparing with the A64FX1. It's only 1 chip, so we compare 2 chips versus 1 chip. And then we are checking the relative power consumption and speed up ratio. And this time I don't show the speed up ratio here. I'm sorry. This is the graph for the speed up ratio, and almost the same result comes out compared to 2 chips. 60 to 70% faster. So in other words, compared to the chip basis, it's 2 times or 3 times better performance. And the OpenFOM or Abinet, as you see, various type of HPC applications are available, and they have multiple patterns of calculations. And whatever the pattern is, compared to general purpose CPU, a 64FX has a better performance twice or three times, and 3 times better power saving. And also with this high density model. So ordinary data center, normally one rack has one U or one node. Most recently, we see more high density package, but roughly 80 to roughly 40 nodes or 80 chips. And most recent high density type, it's a double to that. But in our case, more than double than that. So that means one rack has 384 nodes installed. So each rack has over petaflops performance. And to achieve this density, it has a complete water cooling system, and it's a 2-node system. So the blade 192 blades are installed. So the rack configuration is very important because it is important for the interconnect network. And this TOFU has the 6D mesh torus network. And on the right, in our network, DMA controller directly connects with network on chip. So that means that the packet can be put in L2 cache directly, or that can be a cache injection. Through that, very, very super low latency network is feasible. How low is the latency? For instance, ordinary 10G, 40G Ethernet network, it takes roughly dozens of microseconds, but Fugaku, it says 0.5 microsecond. So that is latency drops to 1 over dozens or 1 over 100. So in terms of the bandwidth, we calculate like close to 40 gigabyte per sec, so 400 gigabit size of the network. An ordinary data center, so one data center, how many 400 gigabit will be available? Or most recently, 1 terabyte, how many terabytes are coming? But in our case, 160,000 nodes, each node has 400 gigabit. And overall network bandwidth of overall Fugaku is 10 times bigger network capacity, accommodating all hundreds of data centers traffic around the world combining. So including hyperscaler like Google, Azure, Amazon, and others. So that, 10 times to combining everything. That capacity of supercomputer, the capacity of supercomputer is that big. So this is 158,976 nodes. This is a performance list, so you can read this in a specification later on. But the key message is that in case of 64 bits, roughly 500 petaflops level. But in case of single precision or half precision, the performance surpasses exaflops already. And then on top, memory bandwidth exceeds 150 petabytes per second. So this tells you compared to traditional supercomputer, Fugaku is faster in terms of absolute performance and catalog performance. The question is, the performance can be exercised in an application or benchmark. So first half result of twice a year supercomputer performance ranking is released at the ISC 2020 in June, Frankfurt, Germany. At that, Fugaku became world's #1 in not only one benchmark normally covered in newspapers, but all the benchmarks rankings, especially HPCG benchmark, not just the top 500. This HPCG new benchmark. This is a conjugate gradient method, and in case of manufacturing, this benchmark is more important than others. And in case of AI, the HPL-AI, that is a representative of absolute performance of the convolutional kernel, and the big data graph 500, and the breadth first search, in graphic processing, all rankings we became #1. And the margin of the difference, in case of HPC-AI ranking, 1.42 exaflops was achieved, and #2 ranking was a US or Chinese traditional top supercomputer. We had a margin of 3 times or 5 times outperform. This is very important because across all the benchmarks, we have to be #1. Otherwise, it is not the machine we proclaim to reach the application first, because benchmark is the one element of the applications. So to be the application first machine, we have to reach #1 across all the benchmarks. So assuming top 500, yes, we became #1, but other benchmark we failed to be #1, then it's a failure of our development. Luckily or fortunately, my machine achieved #1. So compared to the pre-exascale machine, for instance, US or China machine is a exascale, but we are ahead of that. So our machine is, fair to say, exascale. So, as I said, the performance is splendid, but the versatility means because the Fugaku is the ARM server, so from the user perspective, it's the gigantic Linux class server, not more, not less. Therefore, as you see on the left, this is the typical type of standard stack, and at the bottom, the compiler, debugger, parallel language or parallel libraries, and so forth, many libraries, and so forth, math libraries as so forth. And not only on top, as OS, for example, Red Hat Enterprise and Cloud Software Stack are supported in Fugaku. And OpenStack, Kubernetes, and data analytics engines are supported on the above layer, and at the lower layer, KVM, Singularity containers, as well as virtual machine technology are all installed to significantly improve operational versatility by virtualization. Therefore, traditional supercomputer software stack and the current cloud, big data, AI software stack will coexist on Fugaku. This coexistence is realized in a very natural way. Hence, Fugaku's high performance is very well realized in simulation, big data, and also in AI. But there are a few difficulties in AI, which I will comment later on.
And because it's high versatility, so there are various ISV applications. So they are already running, or each ISV company is now coding. And those applications can be accessed via cloud. So we collaborate with various cloud providers. There are large ones and also small ones specific to HPC. So we collaborate with them. Even the HPC cloud service and also the integration with the conventional services would be provided as cloud service to all Fugaku users, so that development can be done as part of cloud ecosystem. If we can do that, well, those are the commercial machine. The prime HPC FX1000 is Fujitsu's commercial machine. The left-hand side is the same as Fugaku. It's a high-density supercomputer. The right-hand side, well, it's a little hidden, but it's a regular server form factor, and it's air cooling. And the network is not TOFU. It has InfiniBand, and if necessary, 10G or 100G Ethernet can be attached. So such a versatile form factor is developed by HPE Cray company. And the FX1000, the same format, same type of machine is installed in several locations. And they are mainly small or medium-sized machines. And more it is installed as a 2U rack server. As for AI, I said that it's a little tricky in AI because, well, Fugaku, in terms of potential performance, it could be the top AI machine in the world because each CPU Well, we couldn't install matrix engine, but it's been expanded for vector type, so it has a performance equivalent to mid-range GPU. FP16 and int8, where the performance that is used for deep learning, it's supported. So it's very high performance. And the large-scale AI is HPC. So it uses supercomputer to learn. So that's the latest technology. And even Microsoft has just recently issued a press release the other day that they developed supercomputer that could be one of the top 5 in the world, and that will be used for their AI development. And it consists of CPU, GPU, and machine, and they put them in Azure environment, and they use this for their AI development. So the top AI development cannot be done without supercomputers. And those supercomputers have to have high AI capability. And Fugaku has very high CPU, and the network is very high speed. So the large-scale deep learning can be done on Fugaku. And the power is shown here. Well, we don't know the infrastructure that is in one private company. So those are the list of machines that are in the public organizations, such as AIST or NICT, or those national organizations. So large GPU machine that has high AI capability. So this is a list of those supercomputers. And even if we add those up, and that includes Tsubame or AICC that I was involved in the development, but it's only a fraction compared to the summit that is in the US Oak Ridge National Laboratory. However, Fugaku, compared to Summit, has several times higher deep learning processing power. The question is how the users should be able to use this power and for what kind of applications. So we have a research team at our center. So the challenge is when training is done on Fugaku, the challenge is to scaling DNN training to 100,000 nodes on Fugaku. So the learning or training at each node have to be at high speed. In case of GPU, NVIDIA have spent many years to improve architecture, but also developed the CUDNN, that is a library, and PyTorch or TensorFlow for deep learning framework would call this cuDNN functions when computing. The same thing have to be done with A64FX, and that development was very hard. Even if we were able to do that, the large training would require data parallelism. And conducting large training means the network is large or data set is large. So it takes up a lot of memory. But each GPU or each A64FX memory is limited. It's only 32 gigabyte, and the latest CPU is only 16 to 48 gigabytes. So the large network or large data set cannot be handled with those. And another challenge is the convergence issue. It's too technical, so I wouldn't go into the details. But if you achieve a large parallelism, it's very difficult to converge the learning. So how to converge would be another mathematical challenge. So by conducting various researches, we are developing the largest scale AI learning on Fugaku. And on the bottom, we collaborate with Fujitsu and ARM. And the DNN that was developed for Intel, it's called 1DNN. And we are revising that and optimizing that for ARM. And with that, the PyTorch or TensorFlow for Intel can be optimized for ARM. So one DNN library optimized for ARM, and the scalable development can be done.
So in fact, we run to have development in advance, and the development version is already on the open source. So by measuring the learning performance or scalability, learning performance has achieved mid-range GPU level. It is very scalable. As you can see, a number of nodes is increased from 2, 4, 6, and 8. The more node we have, the faster the speed of learning becomes on a linear basis. Then the challenge question is that what happened? The number of nodes is increased more. Well, we observed learning scalability up to 27,000 nodes. So this level of massive learning is done on Fugaku. We can do the AI training that in the past was never achieved. And on Fugaku runs HPC simulation as well. So by combining these functions, HPC and AI harmonization, we'll be able to design new things. For instance, in designing a new car, the simulation will be done on Fugaku, and the forms will be considered. And that simulation is optimized, of course, and that process can be done together with the AI and HPC. So, and the new type of designing, new type of engineering will be feasible. And then quickly, for example, so this aerodynamics of automotive are very important. Because of fuel efficiency, we have to have air resistance or pneumatic resistance. Smaller. And of course, at the time of the crosswind blows, the car must be stable. It also has a requirement of good looking nice in order to sell a car. And those requirements will slightly change the form of or design of the car. And one may not fit all. And as a designer in the past, human designer has to, scrape the clay model or wind tunnels, and took so long to redo everything. However, not only inputting those aerodynamic conditions to output designs, but also put humans' sense of beauty into AI, so that everything is optimized, and then that kind of design, automatic synthesization is also feasible. So the sense of beauty of human and aerodynamic related demands or requirements can be blended, and optimum car design will be available. Fugaku enables such an approach. And finally, how Fugaku is combating new COVID-19. And Fugaku will not be officially operational until April next year, but we are now in the middle of the test installation. And of course, COVID measures is a very key topic. Therefore, we kick off this program with Ministry of Education, Culture, Sports, Science, and Technology. And 5 proposals are already available. And most recently, we'll see the 6th proposal. And various analytics and the measures are under consideration. As you can see on the left, capture coronavirus on atom level as well as molecule level, and the elements of the drug discovery and the vaccinations as well as the infectious elements are considered. This is a microscopic approach for medical pharma study. Another element is that the societal epidemiological study and the COVID-19, how it is affected and what kind of social impact do we have. And one example, most of the Japanese audience may have seen on TV, because this is a simulation we did for the many droplet infectious simulations. And this, TV coverage was well received. So some say that the one reason for having Japanese cases relatively controlled, if not perfect, is thanks to Fugaku simulation. And So how to have the drug discovery? It's not a new drug to be developed by. It's not just a developing new drug, but existing drugs over 2,000. We have a variety of drugs like stomach medicines or high blood pressures or vermifuge to kill worms. And this drug repositioning is underway to test the whether existing drugs can be applied for COVID-19. And Dr. Okuno of Kyoto University, with his team and Riken, used the Fugaku to make simulation of massive number of molecules and study how effective those existing medicines would be against COVID-19. Traditional K-computer would require over 1 year to check 2,000 medicines. Again, it takes over 1 year against one protein target. And of course, there are a lot of targets. So it takes dozens of years to complete all simulations. However, Fugaku, each instance is about 100 times better, faster. So it ends within a few days. And as you can see on the left, on the right, this is a pink-colored nicosamide, a vermifuge. It's bonded to a yellow pocket. So in reality, that is a human cell to be bonded and infected. So through this drug action mechanism, it is effective to prevent infection. So, in fact, this is a diagram to show all efficacy of 2,000 drugs ranking. As you see, most of the drugs are plotted on the left bottom, so that is not effective. A drug plotted on the right-hand top would be effective against COVID-19. And niclosamide and also nitazoxanide, that is another vermifuge, and the clinical trial of them are already in place in overseas, but not in Japan, because those are unapproved medicine in Japan. And the efficacy was already reported in overseas trials, but unclear why. But because of Fugaku simulation, this is revealed. And moreover, a drug sold in Japan, though I cannot say the name of the drug, it is developed by a Japanese farmer, which does not have a clinical trial yet, has a big potential for efficacy against COVID-19. It is revealed through this simulation. And another study is led by Dr. Supercomputer of Riken. He is a professor of Kobe University. And droplets are cause of fear because of they are invisible. And there are two types. Big size is droplet, is easily be dropped instantly. And as I am speaking, the many droplets are spreading, or even on my computers. But this blue graph shows this is the micro, the droplets. This is a few micro, very small and less than a few micron. So this is aerosol and spreading around the air for a while. And of course, if any virus content is little because of the size, but it will stay in a room for about a few hours. And here in my room also it's spreading. And we are doing these kind of simulations for a mask too, trying various materials or mask and simulation of wearing for face shields as well. And those simulations of scenarios like who wears face shields or masks, you yourself or your counterpart wear a mask or shield. What will be the impact? And as you can see on the left, a face shield or mask is, of course, a preventive measure for you if you wear. But the bigger effect is confirmed that you will not cause your counterpart to be infected, since most of your large droplets will be captured on the face shield or mask. So that means the social distance can be shorter, narrower. So, but beware that those aerosol or droplets may reach larynx or throats. So, we are now running a simulation. So these are the studies underway with the multiple corporations. And for example, the Suntory Toppan, a new type of face shield is developed, which while dining and drinking safely, so that we'll be able to help restaurants industry. So that concludes my presentation. I appreciate your ongoing support on Fugaku. Thank you.